Greetings everyone. Today we're going to explore graphing functions from a table. Make sure you have your note sheet ready because what we're going to do is we're going to create a table of coordinate values. And when we plot those dots onto a graph, we're going to get one of these types of graphs. Let's go over some steps. It's up to you if you want to write these down nearby in your notes. The first thing we have to do on some of our functions is isolate the output, or the y. We need to find out what's our rule. We're going to use or choose at least 5 x values. A lot of times we're going to start off by giving those to you. You're going to plug those x values into the function. And I'm going to say rule because we've been talking about rules when dealing with function notation. When we simplify those rules, we're going to get some y values. We'll have dots to plot. And once we connect those dots, we can identify our domain and our range. Let's take a look at this first function. First, I notice that I have a clear rule. My y, or my function notation, is isolated. And this rule is what I want to plug in my x values into. Now, I didn't give you x values on this one, so we're going to stick to the smallest integers possible. We're going to take those integers and we're going to plug them into our rule. So our rule, don't forget, is negative 3x plus 1, which actually means negative 3 times x. And so yes, you are going to write this work 5 times. Why? Because I'm going to do 5 different calculations. And at any point, if you need to pause this video, please do so. So here I left a blank where the x is, because instead of x, we're plugging in negative 2. Instead of x, negative 1. Instead of x, 0. Instead of x, 1. Instead of x2. Do you see how I kept the same rule, but I changed the x? Now I'm going to calculate, and I'm going to get answers. We always multiply first in PEMDAS, so 6 plus 1, 7. We multiply first, 3, 3 plus 1. Multiply first, 0 plus 1. Multiply first, negative 3 plus 1. Multiply first, negative 6 plus 1. What we've done is we've created 5 coordinate values. If I think about the x and y being together, now you don't have to write them down that way every time unless asked, but it does help me visualize my 5 dots. So let's graph them. Negative 2, comma 7, negative 1, comma 4, 0, comma 1, 1, comma negative 2, and 2, comma negative 5. Now in this case, see how perfect that is? We created a perfect line. So in this case, because all we had was some multiplying and adding, this is called a linear function because it made a line. Now domain and range, my line goes forever to the left in the negative direction and forever to the right. If you need help with domain and range, please see that video. Range is bottom to top, where our graph goes forever down and forever up. All right, let's try another one. First, we need to make sure that we have a clear rule. I see my rule. This rule, the y is isolated, or the output is isolated. Remember, f of x is the same as y. It's my output, okay? So you can think of it either way. For my x values, use or choose 5 x values. I normally would do negative 2 through 2, but look at what I'm going to do. This rule says 1/3 times x. When I times by a third, that's the same as dividing by 3. So do you want to divide 2 by 3? Because I don't want to deal with fractions, right? So first and foremost, you know what the easiest number is? 0. 0 is good to go on this no matter what, because 0 times anything is 0. But I don't want to pick 1, and I don't want to pick 2. I want to pick 3's because I can divide them by 3. I want to pick 6s because I can divide them by 6. Excuse me, by 3. I want factors of 3 because I'm going to divide by 3. See what we did there? All right, let's write our work 5 times. We're going to take 1/3, which is the same as dividing by 3, or use your calculator if you don't understand that. We're going to times it by our x value, and we're going to add 5. So instead of x, we're using these numbers. All right, let's calculate. -6 times 1/3, or -6 divided by 3, is -2. -2 plus 5. -3 divided by 3 is -1 plus 5. -0 times 1/3 is 0 plus 5. 3 divided by 3 is 1 plus 5. 6 divided by 3 is 2 plus 5. And look at that nice pretty pattern we have there, right? So let's graph. This time I'm not going to write them out. We're just going to plot our dots. -6, +3. Now if your graph is too small and this dot doesn't fit on there, that's okay. Then let's move on to the next one. -3, 4, 0, 5, 3, 6, 6, 7. If you can't fit that last dot, not a big deal, because even if you only have 3 dots, you have enough information to connect. You have to draw arrows. Arrows imply that this graph goes forever, which it does, right? If my table keeps going, my graph keeps going. Now what we just graphed is a line, so this is what we call a linear function. Domain, similar to the first example, forever left, forever right. Range, forever down, forever up. All right, let's take a look at this one. In example 3, our y is isolated, that's good, and I'm going to think of this rule a little differently first. This actually means there's a 1 in front, so I think of this as -1 times x minus 2. See how we have to know that we're timesing by -1. And so when I write my rule, it's going to be -1 times our x values, and then we'll minus 2. All right, so x values, I can times by any numbers. And if I can times by any numbers, let's just pick the smallest integers possible. What that does is makes it easier to graph, and the calculations are smaller. Multiply first. We get 2 and then minus 2. We get 1 and minus 2. We get 0, minus 2. We get -1, minus 2, -2, minus 2. Nice easy numbers, so let's graph them. -2, 0, -1, -1, 0, -2. See how it gets easier to plot the dots because you can see the pattern? That pattern is super important. We always connect and draw arrows. This is our third linear function. It's going forever left, forever right, forever down, forever up. Now let's switch gears here. Here we have something different. First of all, our y is isolated, that's good, and this is our rule. Our rule is to square our x values. And so I'm going to tell you to use the smallest integers possible. And that means we're going to take every x value and we're going to square it. That's what the rule says to do. Now, I encourage you to start with the easiest first. 2 squared. That means 2 times 2. 1 squared. 1 times 1. 0 squared. 0. See my pattern? But let's look over here. Let's talk about this and maybe add this to your notes. -1 squared means -1 times -1. If you type that in your calculator, if you type this in your calculator, you're not going to get the right answer. Why? Because your calculator wants parentheses. So sometimes mental math is faster. A negative times a negative is a positive. A -2 times a -2 is a +4. Okay, be careful. Maybe make these numbers stand out because those are unique. All right. Now this is different. Let's plot these dots and see what happens. -2, 4 is here. -1, 1 is here. Oh, that's different because now 0, 0 is here. 1, 1, and 2, 4. My change isn't the same, right? It's not constant. Like we jumped by 1 and then we jumped by 3. And so what this means is this makes a perfect U shape. Yes, it needs to look like a U, curved, since the change isn't constant. And so we call this, so in this example, this is really your notes. This is what we call a quadratic. I wrote a little too big there. Let's try that again. Quadratic. Anytime you have a function where the degree or the highest exponent is 2, it's quadratic. And every quadratic U graph will be a U shape. U shape. Can you make that note somewhere? Maybe just say U shape somewhere. That's very important. Write that down. So domain and range. You've actually did this in the domain and range section. Forever left, forever right. Range, however, we go forever up, but I don't go forever down. Do you see my border here? That's as low as I go. Or look here. The lowest y value where I exist is 0, and I exist there. I need a bracket. Every squared function needs to be in the shape of a U. Let's try another different type. This is what we call an absolute, and I'm just going to start with that. Let's fill in the type. This is an absolute value function. Ooh, sorry, my handwriting's horrible today. Absolute value. All we're going to do, that's our rule, right? This is our rule. Absolute value. When you draw these absolute value bars, which I am not doing well today, please make sure they are bigger than your normal handwriting. What I mean by that is I don't want it to look like a 1 or an L. Okay? Now we're going to take our smallest integers, and instead of x, we're going to replace x with our integers. Now, if we were to look up the value of it, or excuse me, the definition of an absolute value, it is the distance from 0. And so 2, the distance from 2 is 2. The distance from 1 is 1. The distance from 0 is 0. But watch what happens with the negatives. The distance from 0, -1 is 1 unit from 0. -2 is 2 units from 0. Meaning the shortcut idea is absolute value causes you to take that final number and get rid of the negative. That's a generic way to say it. We drop the negative of our final number. So let's plot this. What does this look like? We've got -2, 2, kind of easy numbers, right? -1, 1, 0, 0. Ooh, there's a pattern here, and it's perfect. We jumped 1 each time. We jumped 1. An absolute function will always be a V shape. V shape. Can you add that somewhere? V shape. We'll make a V. Okay, write V shape somewhere. So my domain, well, guess what? It's the same as a U, forever left, forever right. My range, well, I'm going up forever, but let's talk about that range. The lowest y value where I exist is 0, and I exist there. There's a dot there. I exist from 0 to infinity on the y-axis. Okay. Can we just talk about absolute one more time? Down here at the bottom, if I was to say negative 3 plus 2, okay, we would treat it kind of like parentheses. We'd take care of the inside first, and then we drop the negative, okay? See how that changes my answer? Inside first, then drop the negative. Okay, you're going to see some more like that, so don't forget that. All right, our last one. I am going to have an exponent, and so I'm going to stick to an x value of 0. Oops, first, my apologies. Yes, y is isolated. Here's our rule. I can take a first for an exponent. I can do 2, and we're going to try these negatives and see what happens, okay? You're going to need your calculator. Please, please, please know how to type this in your calculator. So for my rule, I'm going to take a base of 2, and every exponent is going to be x. See how I wrote them small? Let's do the ones we know, right? Easy numbers first. 2 to the first is 2. 2 squared means 2 times 2, which is 4. 2 to the 0, please type that in your calculator. 2 to the 0. If you type that in, you get 1. Now, you don't have to have that rule memorized yet. We'll do that later. For now, you got to use your calculator. And guess what? If you type in 2 to the negative first in your calculator, we get 1/2 or 0.5. Wait a second. Let's type in 2 to the negative 2. That caret top is a key on your calculator, right? We get 1/4 or 0.25. Huh. See the pattern? 2 versus half, 4 versus fourth. If you had to guess, next would be 8 and 1/8. Next would be 16 and 1/16, right? Like that pattern would continue. Interesting. Okay, let's plot our dots. Negative 2, 1/4. Oh my gosh, that's so tiny. It's almost right above the axis. Negative 1/2, a little easier. 0, 1. 1, 2. 2, 4. I'm going to plot. I have room for the 8. You probably don't, but 3 would be 8. Now, before you connect your dots, can you hold up your hands? Because what we just created, we created the curve of our hand. Meaning, let me explain this further. If I was to go to 1/8 and 1/16 and 1 over 32 and 1 over 64 and 1 over 128 and 1 over where am I at? I already lost track, right? It's going to be tiny fractions, tiny, tiny. Does it ever turn negative? It doesn't. That means we cruise along the x-axis, and then all of a sudden we kind of like go straight up for this graph. See how that's the curve of your right hand? It could also be the curve of your left hand, depending on the numbers given. Okay, we call this an exponential function. So let's talk about the domain. This graph is forever going left, and it is forever going right, right? I could plug in x values. They're going to be really steep, but I could keep going. Range, it's going forever up for sure, right? But range, the bottom range, is 1 my smallest number? No. Is a half my smallest number? No. Is a fourth my smallest number? No. But what am I approaching? What am I getting closer to? I'm getting close to 0, but I'm never going to be 0. Can you make that an annoyingly obnoxious parenthesis? We're getting close to 0, but we'll never be 0. Now my little, I don't know, memory, silly thing, little trick, whatever you want to call it, shape of hand? Like, could I say that? Or curve of hand? Maybe I should say that. Curve of hand? Would that be better? Whatever way you can remember how it should look, okay? Fractions and decimals are okay. All right, so a couple of strategies. If you've been writing this whole time, please consider just listening. consider just listening. All right? What I mean by that is sometimes we don't truly understand things by just watching once. If we re-listen without being distracted by other things, I might understand it better. Okay? Also, make sure to check out Google Classroom. What's the task to go along with this lesson? Make sure you seek out support in the Sabre Center. Let me know if you have any questions, and until next time, have a good one.